we have learned a lot, and this is now the last two talks to begin. And don't rush, I can speak for as long as you want, James, to introduce.
I don't doubt it.
Tim Dion is also from OCL, and will explain to us first order logic for small-talk module reasoning. So I'm aware of first order logic. That was what the other people didn't do in Smalltalk. And it took them 2 weeks to fix this minor problem in their software. So I'm curious what you did with first order logic, whether it's also bad or good.
Well,
we'll learn about it.
They should have written the first order logic in Smalltalk.
I told them.
First of all, I have to ask, are there any logicians in the audience today? One? Okay. I have to, two? But I have to know how much hand waving I can get away with. so there'll be a fair amount of hand waving. So, what's this presentation about? And the basic idea is, if you have a large system, how can you reason about your modules? And normally in a system like C, Make does a lot of the work for you. But we don't have some of those luxuries of things like Make. So what this presentation is about is using first order logic to basically reason about system dependencies. So a quick overview. I made too many slides, so I'm going to go through some of these rapidly. Just ignore this. If anyone's curious, I made my slides in Beaver. It's a LaTeX PDF tool. It's really nice. So a little bit about Iris 2. Iris 2 is a very large software application. It runs Smalltalk and Gemstone. Iris 2 is big, and I define big as 3 million lines of code. It's really big. We support 2,000 concurrent users, and we have 2 billion persistent objects in our Gemstone database. So our database gets very large. So a group of us were tasked with porting Iris 2 to Visual 7. And of course, this means moving from store to NB, which causes several problems. The biggest problem is that the concepts don't align very well. So bundles, as I'm sure a lot of you know and figured out painfully, that are not configuration maps. And packages are not the same as applications. And the biggest problem we have is that NB loads configuration maps atomically. So it kind of figures out, and we'll work around prerequisite issues. And Store doesn't. Store doesn't load bundles atomically. So that means that packages that live in bundles have to be well ordered. You have to put them in the right order. And we also looked at a model, our export model, where we collapsed NB sub-applications into one package. So the problem arises is that has NB hidden problems in our dependency chain? More specifically, does every superclass live in a dependent application? Well, there are more complex ways of saying that, more precise. So the basic issue is in the blue we have a normal load order, and the objects you can think of as classes. But the question arises, are our prerequisites correct? If NB's hidden something, do we have classes that are loaded incorrectly or in wrong order, or bad prerequisites? Even worse, we have missing prerequisites. We have classes that are referenced in a class that don't live in the dependency chain, prerequisite chain. So the problem is, again, Iris 2 is huge. We've got 8,000 classes in Iris 2. So, why wouldn't we just graph them out? Well, zoom in here. Because it would take 12 feet of paper. And it would take a long time sitting there with a pen, trying to find if all the dependencies are right. So clearly we needed an automated way to reason about application prerequisites. The manual approach would take weeks. So before I can talk a little bit about the solution, I need to introduce first order logic. And so I'll try to give an engineer's introduction to first order logic, which would be like the way a programmer would learn a language. And the way I learned first order logic was in a program called Tarski's World, and that was for a graduate class. And it was part of this book here, which is John Barwise and John Etchemy. And these are two guys at Stanford who wrote this program for teaching logic to graduate students. So the basic idea behind Tarski's World is that you have a chessboard, and you have shapes in the chessboard. And then in the field on the bottom, you write in expressions, and the system will evaluate whether the expression is true or false. Tarski's World also gives you a number of predicates to reason about things that live in the world. So you can talk about shapes, positions, and size. So if I can start with a real quick introduction, I'll start with quantifiers. Quantifiers generally sit outside. And the upside down V says that something is true for all elements in your domain. So in this case, we have the statement, all things are small. And in this world, you can see that that's not true, because there are things that are not small. Talk a little bit about the existential quantifier. It says at least one thing is small. And of course, that is true in the world, because there's at least one thing small. And of course, we have the standard logical operators. You're all engineers, so I think you understand these. But we can start off with no item is small, so the not can go in front of the expression. One item is small or large. That's probably pretty straightforward. One item, at least one item, is small and large. Now, that sounds like a contradiction. It turns out in this world, it is a contradiction, but it's actually a valid thing to say. It's just unsound. So you can imagine worlds like Lewis Carroll did, where you have things that are small and large. So there's a certain border of soundness where your predicates talk about things inside the world. And of course, we have the one more operator, which is the if-then. So all items that are small must be tetrahedrons, is what that says. So a predicate is a kind of relation, but the important thing about predicates is they describe things that live inside the world. So predicates are sort of your interface to the world. Now I've talked a little bit about first order logic. Hopefully you get a sense of what you do with it. The project that I did is essentially an expression evaluator for Smalltalk, which lets you reason about things that live in Smalltalk. In our case, especially, that's classes and applications. So like Smalltalk, like Tarski's world, you can write these expressions and evaluate whether they're true or false. Just an important note that Smalltalk is not a FOLIE is not it's not a theorem solver. It doesn't let you build complex predicates, and it doesn't let you define premises. So it's just evaluates things that live in Smalltalk. That's all it is. These are the predicates. They're pretty straightforward for reasoning about subclasses, packages, references, and prerequisites. And show is a bit of a hack that I came up with for printing to the transcript so you can see what's going on inside of your expression. It's kind of a debug statement. One of the important ones is references. So if a class references another class, we want to be able to reason about that. So if one class is referenced to another, we want to be able to see if that's true or false. And a quick note about the implementation. Basically, this uses SMAC. Is there anyone from Smalltalk or Refactory here? Well, it's a great system. And everything basically maps eventually to a Smalltalk method. So predicates, the handlers, and the quantifiers all map to Smalltalk methods eventually. In the paper, I have a full SMAC style PDF, so the paper should be on the website. And quantifiers are basically just iterators. It's just iterating over the set of objects. So, converting these nice logical symbols into an ASCII syntax was difficult. I had to do some hacks, essentially. But the universal quantifier has a little underscore in front of it. And I had to do some other hacks to get things to work the right way. So essentially, a literal, like a package name, as we have a package here, kernel, is basically a literal. And this statement says, all subclasses of kernel must live in a prerequisite package. And we have to basically have all the conditioners. We also have equals and not equals, so those turn out to be necessary. And I also use the C-style syntax for Boolean operators. So that seems like a lot of work, just to reason about packages. But the important thing is that now I have a generic query language where I can talk about other problems and other cases in Smalltalk. I can add predicates, so we can talk about other relations in Smalltalk. We can say things like all concrete classes should have an abstract class, for example. And one of the interesting areas is that we can have a design that specifies constraints in the design as in UML, and then you can verify that those constraints are met in your runtime system. So you can do this sort of validation of your system. And even more interesting cases is that you can have abstract designs that get validated by your concrete implementation. So the things I'd like you to take away from this is that first order logic is cool. It's neat stuff. It's not very hard, and it's a very compact way to describe things and relations. And it's good for doing automated reasoning. I guess I went a little fast. Any questions?
You talked about the evaluations that you're doing to confirm that a reference class existed in the list of the existing list of prerequisites.
Yes.
Do you ever go to the extent of confirming that a called method is defined by a class in the prerequisites?
Did everybody hear that? So the question was, do we check if called methods are referenced in classes? Currently, the system doesn't, but you could add a predicate fairly easily that does that kind of reasoning. So yeah, you could do that.
That's actually not required to make overload happen correctly, because if the method's called, that won't happen until runtime. It happens after you load it. So usually that's less, at least in my experience, that's been less of an issue. Basically, we don't care whether or not it's in a prerequisite or not. It could actually, the method could be defined as soon as loaded later. As long as they're all, in fact, all loaded. That's effective zero.
But I think that one of the point about that might be well taken is that in the sense that you could then make sure that the things that are not called, so that it was very easy to write the predicate, do the checking, then you could do some other evaluation at runtime or something to make sure
Right.
where they were.
Yeah. You could make sure that the things that needed to be included were included. Right. But the more strict includes the order, so the other includes the totality of what happens. Right.
We had a question in the back.
I just want to comment to that. It seems like you can only do that easily in basically a self-setting where you're doing your own type of proceeding, because otherwise, how do you know what I have in variable X? Right, so I'm saying X n.
If you know who your prerequisites are, you can examine every method call in your methods in that package, and go up your prerequisite chain and check each of the classes in the prerequisites. And if that method is defined somewhere in the prerequisites, then you know that your prerequisites are solid, at least for the methods that you're going to call.
So my point was that you don't know the type of proceeding of the class.
Yeah. So you can only detect the complete absence of the method in your prerequisite chain. You can't detect whether it's defined in the right place.
True.
Just define whether it's defined at all.
Right.
I hope that at least in these areas, suspects that there isn't.
Question in the front.
So I've noticed that you've expressed your predicates kind of like a small talk method. So can you create essentially higher order logic by...
The question was, can I create higher order logics, which would be like a second order logic? Me personally, no. I couldn't, but
I guess if you contextualize your predicates, you can, right?
Well, in second order logic, you have to reason about relations, so you have to add relations to your grammar, and that becomes a lot more complex. And second order logic is incomplete, so you can have expressions that you can't solve, basically. So most logicians think that first order logic is sufficiently expressive to handle everything we want to talk about. So, in our case, I don't need to model relations, so and second order logic is much more difficult. But somebody could potentially do that. Any more questions? Oh, one more.
So are you going to apply this into the domain area at OOCL?
Yes, yeah, we've already used it to find out all the problems in our port.
Oh, that's like system stuff. I mean, like in the application area, domain, in the business.
There is a possibility of doing that. We've talked a little bit about actually, not so much in our domain, but in our build release configuration management process to verify that our packages are well formed, essentially before we were built. But we haven't really talked about the domain ring. The problem is that try to evaluate an expression over like 9 million objects. You use up all the memory in gemstones, so you have to use job workers or some other mechanism breaking this down, but it could be doing it. In fact, I'm new to gemstone, and last year I actually tried that to iterate over 9 million objects, and it used up all the memory in the system.
Temp space, or what kind of memory?
Oh, yeah.
Yeah.
You have to do micro theorems.
Yeah. We have a job manager that will break a job into pieces and execute the pieces.
Why did you decide to go for the ASCII representation in your graphic
Yeah.
representation? I will comment to you. So using visual works, I just tried it while you were speaking. You have a chance to do the real signs like the for all,
Yeah.
and you can have the support to type them like alt 8,800, 704
Yeah.
to get the real signs, and it all works.
Well, to be usable, I'd really have to make a user interface. And I just
Yeah,
need
in the user interface.
Yeah. Well, you need something like FOLIE has, is a complete user interface for entering all the characters and all the predicates. So to make it really usable and easy, I'd have to do something like that. But yeah, I could have used the big characters. But I was just doing a quick project. Any more questions? Well, great. Thanks a lot. It's been fun.